Have you ever stared at a really complex problem and just wished you had the perfect tool to crack it open? Well, when it comes to algebra, dividing polynomials is exactly that. It's a power tool that can solve problems in design, engineering, you name it. So let's dive in and see how this thing really works. Okay, so imagine for a second you're a designer. You've got this exact area of paper for a book cover, right? And it's represented by this polynomial. You already know the length, you know the spine dimensions, the whole deal. The only missing piece of the puzzle is the width of those folded flaps on the side. This isn't just some random math problem, it's a real-world design challenge, and polynomial division is literally the key to solving it. Now, before we tackle that book cover design, we've got to start with the fundamentals. We're going to ease into this because the simplest type of division actually builds on skills you probably already have. Think of it as a good warm-up. So this first method is called division by a monomial. And I know monomial sounds like a fancy word, but all it means is a single term. The strategy here is a classic: divide and conquer. We're just going to break down one big, intimidating expression into smaller, way more manageable pieces. The trick is to stop looking at this as one giant division problem. Instead, you can reframe it as three separate, much simpler fractions. See, we just take each term from the top polynomial and put it over the monomial we're dividing by. It's that straightforward.
And boom, just like that, you see how powerful this is. We handled each little fraction one by one, applied some basic exponent rules, and out pops this clean, simple answer. Each part was easy, and putting them all back together gives us our final result.
All right, let's grab the next tool from our toolkit, the classic long division. This one is a universal method. It's like the trusty all-purpose socket wrench that works on pretty much any polynomial division problem you can throw at it. So, does this whole setup look familiar? It absolutely should. Believe it or not, the process for dividing polynomials is almost identical to the long division you learned with plain old numbers way back in grade school. The steps, divide, multiply, subtract, bring down, they're exactly the same. We're just swapping in some variables now. The key is to just trust the algorithm, right? First, you divide the leading term inside the bracket by the leading term outside. Then you take that result, multiply it by the entire divisor, subtract that whole thing, and bring down the next term. You just stay in that loop, divide, multiply, subtract, bring down, until you're done. So after running through that cycle, we end up with a really clean answer, x plus 8, with a remainder of 0. That's a big deal. It means that x minus 5 divides perfectly into our polynomial. It's a factor. And you got to admit, it's so satisfying when it works out perfectly like that. But you know, life isn't always perfect. What happens when things don't divide so cleanly? Just like with regular numbers, sometimes you're going to have something left over. So what do we do with the leftovers? Well, the rule is actually pretty simple and kind of elegant. Your final answer is the quotient. That's the main answer you figured out, plus a fraction. And that fraction is just the remainder over the original divisor. This little formula right here is your guide for every single problem that doesn't divide perfectly. Let's look at a real example of this. When we try to divide a squared plus 7a minus 11 by 3 minus a, we go through all the long division steps, but we hit a wall. We can't get to 0. We're left with a 19 at the very end. And that, my friends, is our remainder. So here's how we put it all together using our rule. The main part of the answer, the quotient, is negative a minus 10. And then we just tack on that fraction, a remainder, 19, over our original divisor, 3 minus a. That is the complete, totally correct way to write out the final answer. All right, now that we've gotten the hang of the universal tool, it's time for an upgrade. Let's check out a specialized, super fast method called synthetic division. It's an amazing shortcut, but there's a catch. So synthetic division is this awesome, streamlined process that completely gets rid of the variables while you're working. It just focuses on the numbers, the coefficients. But here's the catch, the big limitation. It only works when your divisor is a simple little binomial in the form of x minus r. That's it. Just look at how fast this is. You write down your coefficients and the r value from the divisor. Then you just get into this simple rhythm. Bring down the first number, multiply by r, add to the next column. Then take that result, multiply by r, add to the next column. You just repeat that quick pattern all the way to the end. And the magic happens in that final row of numbers. Those are the coefficients of your answer. You just have to fill the variables back in, starting with a power that's 1 less than what you started with, and that very last number on the right, that's your remainder. In this case, it's a nice clean 0. Okay, but before you get too excited and try to use this for everything, you gotta remember the rules. Seriously. The divisor has to be in that x minus r format, the coefficient on that x has to be 1, and this one is so important. If your polynomial skips a term, like it goes from x to the fourth straight to x squared, you have to put a 0 in as a placeholder. If you follow these rules, this tool will save you so much time. So we've looked at 3 different methods for dividing polynomials. The real skill, the thing that separates the pros from the beginners, is knowing which tool to pull out of your toolbox for which job. Let's do a quick recap. This table pretty much says it all. If you're dividing by just one term, the monomial method is your best bet. It's fast and easy. If you've got a complicated divisor, or if you just want a method that is guaranteed to work every single time, long division is your go-to. And if you get lucky and your divisor is in that special x minus r form, synthetic division is going to be the fastest way to get the answer, hands down. And remember, this isn't just about passing a math class. These tools are actually used to model situations in the real world. I'm talking about things like figuring out the dimensions of a shipping box, analyzing currents in a physics problem, or even building financial models in business. The ability to work with these complex expressions is a surprisingly useful skill to have. So, I'll leave you with this final thought to chew on. We know division is just the opposite of multiplication, right? And we saw that when the remainder is 0, it means the divisor was a factor. So now that you have these power tools for division, think about how you could use them in reverse. How could you use division to hunt for the hidden factors of a really massive, complicated polynomial and break it down into its fundamental building blocks? The possibilities are pretty cool to think about.